Well, excellent. Good morning and good afternoon, everybody, depending on which part of the globe you're located. This is Bob McQueen with H3B Media, welcoming you to the Positive Thinking web conference on machine vision. We're absolutely delighted to have a stellar panel of experts here today, so I won't speak too long. We'll get on with the good stuff. But I do want to point out that copies of the slides will be made available. You don't need to ask that question at the end. We're taking questions via chat at any time during the session, during the speakers. We'll allow the speakers about 8 minutes each to say their piece at the beginning, and then we will ask the questions at the end. We have a wonderful panelist lineup today: Jim Kennedy, who's the Chief Executive Officer for INRIX Zamir; Eddie Vermeulen, Product Manager from FLIR Trapicon; Eric Taufan from Citylog in France; Todd Creter, VP for Product Development for Iteris; and Frank Long, who's the Director for JAI Traffic Solutions. And machine vision is absolutely fascinating as a subject here, because we have the opportunity to use cameras to see things and also to do counting and classification and recognize things. And it's an absolutely wonderful subject area with a lot of room for growth and very exciting technology developments. So without further ado, I'm going to hand over to Jim Kennedy, who's the CEO for INRIX Zamir, and he will go through his presentation. Jim, over to you.
Thank you, Bob, and hello to everybody who's attending, if indeed anybody's attending. My thanks to Bob, of course, and Gareth and Kevin Boris for putting this together. Could you give me the first slide, please? Okay, I'm quite sure everyone on the call knows to one degree or another what machine vision is. Essentially, it's using an electronic set of eyes to inspect, to grade, evaluate, or approve and even reject items passing the field of view of a camera, which is the electronic set of eyes, and to do so at a greatly increased rate of speed, well above the capability of a human being. The point is to save time, increase productivity, and hopefully reduce the error rate. Slide, please. Here's a very simplified, and it's very extremely simplified, so I apologize for the simplicity of it, but a very simplified industrial type of machine vision system as I envision it. The sensor on the right, that little blue box on that silver column looking down at the box, acts as a trigger. It detects the presence of a package on the conveyor belt, and the second sensor, the blue box below it, scans a barcode on the side of the package. The trigger told the second sensor it should see a barcode within a certain period of time, and pretty straightforward in this simplified view. So how can it be applied to transport was the question. Well, it already is and has been for quite some time in the form of cargo container readers, automatic incident detection, vehicle-mounted barcodes for parking privileges and access control, and to me, the more common use would be an ALPR, ANPR system. Slide, please. In this open road tolling view, this application, the first sensor, the one that provides the trigger to the ALPR system, the automatic license plate reader or automatic number plate reader if you're an ANPR person, is anything from a magnetic loop in the roadbed, a treadle, or maybe a laser sensor, very much like the example of the trigger sensor in those packages on the conveyor belt. This trigger tells the second sensor, in this case the gantry-mounted camera, to either capture a series of images and send them to the OCR engine for processing, the optical character recognition engine. This license plate capture or number plate capture system takes advantage of the fact that this plate is a unique identification number available for the camera to see on every vehicle on the road. And this unique plate number can be used as a means of catching violators on a toll road, or perhaps provide travel time information based on the elapsed time a plate is read between point A and point B, or even providing origin and destination study data for highway agencies, any number of uses. So an ALPR system, a roadway machine vision system, if you like, is creating vehicle data in real time for whatever beneficial use can be made of it. Slide, please. So while there are many similarities between an industrial machine vision system and a highway machine vision system, there are also some reasonable differences that have a great outcome on their overall effectiveness. Inconsistent lighting for one, machine vision systems have a consistent and reliable illumination source. Industrial machine vision systems generally allow the operator to flood the subject with light, making much of the process easier, providing depth of focus improvements in that case, or shutter speed improvements, throughput rates, and so on. Systems used on highways do not have that luxury. The sun rises, it sets, clouds roll in during the day, headlights can shine directly toward the camera, and so on. So the challenge is greater for highway machine vision systems. And the illumination issue is amplified because of the distance between the camera and the license plate, which can often be in the area of 50 feet or 15 plus meters for a typical toll road. Unlike the eye, a camera sees reflected light, so the illumination in an ALPR, ANPR system has to travel that distance from the camera to the license plate, be reflected, and travel back to the camera. And in that big open space, that 50 feet or that 15 plus meters, weather can cause problems with the effectiveness of the illumination. Think of fog or heavy snow or very heavy rain. And the slightest vibration at the camera is magnified as well because of that distance. You have to think of how big an arc there is at the top of the mast of a gently rocking sailboat. It's the same effect with a camera that is some distance from the target. So to mitigate that movement, that demands high shutter speeds, which also demands good illumination. And of course, with an industrial application, you pretty much know what each widget is going to look like or how each barcode should appear in that kind of a conveyor belt application. With license plates, you can't be sure of what the color is going to be. Is it clean or is it dirty? Where on the vehicle it's been mounted, and in North America in any event, which one of hundreds of types of license plates it's going to be. Slide, please. Well, what will we see in the next 5 years was one of the other questions, and I think we should see big things. I think a goal of people in the ALPR, ANPR business is to make transponders redundant. And once the ALPR accuracy reaches a certain point, why not just get rid of all that cost, that infrastructure, and that administration that goes along with RFID tags? But to get there, we need to improve the OCR result, and we've reached the point where it's increasingly difficult to gain even single percentage points of improvements. Breakthroughs come as cameras get better resolution, as processors provide more horsepower, and these are ongoing improvements and will continue that way for quite some time. But there are other ways to make the ALPR system easier to lean on, and that could be things like additional parallel applications. Can we determine the make and model of the car, for example? Did we ever encounter this license plate on the same make and model in the past? Yes. Okay, that increases our confidence and that we have it right, that the read is right, and so forth. Or have we seen this license plate before within so many minutes of the current time at this entry or exit or plaza, which is the INEX TAP, time and place system. Based on the number of times,
1 minute left, Jim.
Based on the number of times it's been seen, the current result can be upgraded to a very high confidence that it is indeed correct. We at INEX, as well as others and other folks on this call, are taking a hard look at using some sort of barcode either on or off the plate that gives a much more accurate read and lets you know definitely if you've read it correctly. And there are countries that have a digit on the plate which is a checksum for the rest of the plate, which is a very good way to know if you've correctly read the plate. So advances in accuracy are being made and can be made. And we know from conversations with plate suppliers and also state motor vehicle departments that more and more a good deal of thought is going into the design of their plates in order to make them more highway vision friendly. Slide. And thank you. That's what my last slide would have said.
Wonderful. Thanks very much, Jim. That was wonderful in terms of being pretty much on time, but also a great overview of industrial vision systems and the additional challenges required in the transportation context. Really appreciate that, Jim. Thank you. Moving right along, we have Eddie Vermeulen from FLIR Trafficon, and I'll hand straight over to Eddie. It's all yours.
Thank you, Garrett, and good evening or good afternoon, wherever you are, to all the attendees to this webinar. Next slide, please. Short introduction myself. I'm product manager for an area which we call automatic incident detection in the company FLIR Intelligent Transportation System, but that's probably better known as Traficon to most of the people who are attending here. Traficon, who has been acquired by FLIR end of last year, beginning of this year, in view of the synergies that we see between traffic and thermal imaging, but I come back to that later. For those who don't know Traficon, we have been in video-based traffic detection and data collection and intersection control for over 20 years, so a little bit of a different area than my predecessor, but something similar. Next slides, please. In fact, when we talk about machine vision, there was some confusion when I heard the subject at the first time. There are different ways to interpret the term, and if you come from a production environment, for example, or in a totally different market, I think a lot of people see machine vision as something which is related, just as in the previous slides from my predecessor, which is related to industrial production processes. We think about systems that detect defects in tissues, or look like the picture in the right, at bottles which are filled or not filled properly, so for quality control in a production line of any type. There's a number of things that are pretty typical to these kind of cameras. They have fast shutter speed as first thing. They are looking at things which are moving by as fast as possible, so they have only very limited time to see the object and recognize it. If it wouldn't be a very fast camera, then you would see a smeary picture and not being able to recognize anything at all. They're typically compact design. The output is often a GIGI interface, as it's called. It's something which is related to IP Ethernet, but it's not completely what we know of computer Ethernet. It's uncompressed video, and it's very low latency, so very specific for these applications. And you've got a lot of control on those cameras. It allows the integrator to program them, control them, and manipulate them in very much more ways than some of the traditional cameras allow to do. So next slide, please. If we look at this interpretation, then indeed the application, as said, is probably the most important one, is automatic number plate recognition. There are some very similar facts in that application. We have an object moving in front of the camera. It moves at rather relatively high speed. We have to recognize details in this image without having it to smear around, and we have to process that in a very quick time. So this is typically a number of things that relate to the features and the strengths of those machine vision cameras. We have this fast shutter. It allows us to take different pictures very fast and take the best one and do a recognition on this picture. It has a low latency because often the result of this number plate recognition has to trigger also some other system taking the picture or whatever. We can do processing of the uncompressed video near the processor unit and so on. And we have a tight control on these cameras to tweak the camera parameters just to fit the exact lighting and the exact environment to optimize this application. So the lowest part is a little bit of a generic overview of how these systems work, of how our system works. We have an ANPR camera, we have an overview camera. Consider that as the normal HD typical camera that you know of. And then typically you have some extra lighting, and all these three are controlled by a processing to make sure that we recognize the number plate. So this is the, I would say, the small vision on machine vision. However, next slide. If we interpret this in a little bit of a more broad sense, machine vision, then we could say that you can say it's just visual sensors, not even visual only, that use advanced image processing to support traffic management operations. So then we see a lot of more applications. It's just the camera that helps the operator do things, or that helps the traffic being managed more efficiently. So it's about collecting data, for example, data that's to be interpreted as speed, queue information, classification, how many trucks have passed by, what was their average speed, or what is their average speed, and so on and so on. Second application is more about presence. That's just to see whether you have vehicles standing in front of traffic lights and then give an output to those traffic lights to make them more efficient, so to have a more fluent traffic. So it's a completely different application. A third one is then the incident detection, which I'm specialized in. This is about detecting anomalies, things that should not happen on a highway or a tunnel or whatever critical infrastructure. So to make sure that the operator is warned, he can verify it and make happen an intervention pretty fast. And then the fourth is the one we had just before more, that's more about ANPR. So that's really actually detect the cars and register violations, and that's to support enforcement policies. There's probably a number of other applications, but those are the 4 domains that we are active in. So next slide, please. So if you look at that, what's important for these systems to make them work and to the user, well, first it's about having a high detection rate. Whatever it is, if it is about data or incidents or about presence in front of traffic lights, the system needs to work reliable. Yeah, you have to have a number of very fast, correct detections and not a lot of unwanted alarms or unwanted detections or wrong data coming out. In the end of the story, especially for incident detection, it is a system that supports the operator, so he needs to be able to rely on. If he's in a control center and he gets a lot of alarms or information which is not correct, and I can assure you after 2 weeks he will switch off the system and not use it anymore. So this is very important about the performance. It needs a short detection time. In the case of controlling traffic lights, of course you need to control the lights relatively real time. In the case of incident detection, it's important to see them happen quickly so that the intervention can also happen very quickly. And then, as my predecessor says, that's probably the biggest challenge in the whole machine vision in traffic. It needs to work in a variety of lighting and weather conditions. It needs to work in day, it needs to work sometimes at night. When we talk about night, even there we have differences. Here in my home country in Belgium, we used to have very much lights on the highway, so you could see almost as good as daylight. Nowadays they switched them off as well, and I'm for sure that a lot of countries don't even have lights near their highways. So this is a very difficult circumstance to still detect incidents. You have tunnels, you have
two-minute warning, Eddie. 2 minutes.
Yeah. You have sun, rain, snow, so there's a lot of different conditions that you have to have. It has to be a reliable system for many years because we're talking about long-time projects. And you have to have a flexible interfacing and a reporting to switch into the system. So next slides. I can go pretty quickly. Those are just samples where you can use them. First is the US. This is a system about traffic light control where we detect vehicles. We're talking about thousands of machine vision installations per year really that help traffic go fluently. Next slide. This is the tunnel in Australia. That's probably one of the most critical infrastructures. Tunnels, people are pretty much afraid about incidents happening there, so tunnels is a big market for machine vision and control of the traffic. Next slide. This is the Paris, again about tunnels. We're talking about 1,500 cameras in the whole Paris city region, again to make traffic more fluent and to be able to react very quickly if something happens. As we all know, Paris and a lot of other cities are very highly congested, so it's not a luxury to have some help there. Next slide. And this is a very other side of the world. We're talking about Mumbai in India, where again some sensors are being used to control traffic lights and to make traffic, although it's very chaotic at some times, try to make it go a little bit more fluently and a little bit more in an ordered way. Next slide. So here again also from an Asia country, Singapore is well known for a lot of big installations where the machine vision is used to detect data vehicles and to make the traffic go fluently on highways. Okay, next slide. So that gives you an idea on where those systems are typically used or the kind of environments they are used. If you'd ask me what is going to happen in the next few years or what's going to be new or what is happening, and I'm talking about these points mostly, I see a lot of the systems going for IP video, where we come from typically an analog world. As a reference, I saw last year our revenues were already 33% based on IP video, so it's something which is climbing very fast. I see the trend for edge-based analytics. That's about smart cameras where the whole machine vision is integrated in the camera itself and even recording as well in the camera itself, so you get one integrated unit, what we call NT-Edge, doing the whole job and sending the alarms through the network to any place where it should be registered. I also see some attention for vulnerable road users more. There you see a picture on the right, which actually a combination of the second trend I also want to mention. It's a combination of thermal camera and detecting bikes. So depending on the politics in your country, you see a lot of countries really focus a lot on the vulnerable users, more than they used to do. And knowing some defects or limitations in visual cameras, you also see now some new projects popping up that are open to using thermal cameras or thermal vision, which have the advantage to see in bad weather conditions. And then the fifth thing that I see is the increasing resolution of cameras. It's something you see in every security exhibition, and if you think about our world, and what you see is most of the trends and technologies arising in security exhibitions, they pop up typically 2 years later in the traffic world as well. And that's exactly what you see nowadays. So I think that's the last slide. So thank you for your attention, and back to you, Garrett.
Great. Thank you very much, Eddie. That was great. Thank you for adding the global dimension and giving us a view of the future. I got to tell you, the machine vision application, looking at how much is in the bottle, is dear to my heart. Being Scottish, I want to make sure that exactly the right amount is in the bottle before I part with my money, but maybe that's a Scottish perspective. Anyway, I think we're up with Eric Tofa next from Citylog. Eric, are you there?
Yep, I'm there. Thank you.
I'll go to hand over to you now.
Thanks. Welcome, everybody. Good morning or good afternoon, depending on where you connect from. Next slide. I wanted to have a quick focus. You can go next slide. Yep. I wanted to give you a perspective on 3 different range of applications for machine vision applied to transportation. So the first one is intersection control, where we can use machine vision in several different ways. One of the ways we can use machine vision is loop emulation, which is the top right image, where we basically use virtual loops instead of embedded loops. And the rationale for that is really to get rid of the constraints imposed by embedded loops by providing a more flexible solution, a solution that will have less constraints in terms of installation and maintenance. And something that is little known is a better availability of your detection and intersection control infrastructure over the years, because you will have less failure rates with machine vision than you will have with loops. So that's that first application is really an embedded loop for a virtual loop with no change in the functions. Exactly the same function, but different means of providing that function. The second way we can do we can apply machine vision is the second picture, and is really by providing queue length using exactly the same kind of hardware, which is either a camera and a processor, or what we call a smart sensor, which is basically a CMOS camera with processing power running the detection algorithms. But using exactly the same hardware, same installation, we can provide more than just presence detection, and that is a real-time queue of vehicles at the intersection. The advantage of doing that, and you can see on the example, on the picture, on the snapshot, that the detection zone is much longer, up to 100 meters, 300 feet. The advantage of measuring the queue is that we have a direct measure of the waiting time, and by optimizing the waiting time, we can reduce that waiting time overall on the intersection and directly reduce the emission of greenhouse gases and pollution. And using the same kind of sensor, the last example is providing anti-gridlock. That's the bottom picture, and the anti-gridlock is really to make sure that by detecting standing vehicles at crucial points of the intersections to make sure that the traffic never gets gridlocked, because we're going to detect pre-gridlock situations. So that's a system, this example is in Paris. That's a system that's been installed to make sure that the tramway always would be able to run not only at the green light, but would be able to run through an empty intersection. Next slide. The next range of application is automatic incident detection, which is detecting incidents or accidents on roadways, whether it's a freeway, it's a bridge, or it's a tunnel. It's a security and safety system, because by detecting quickly an accident, you can assist people very as quick as possible, and possibly save lives of people who are involved in the accident, or prevent a secondary accident. But also it's a mobility system, because a standing vehicle, like you see on the picture on the left, on the ring road or on the freeway, maybe not is not directly a safety or a security hazard, but is a mobility problem, because it will slow down traffic, it will create incident-induced congestion, and you want to tackle those as soon as possible. Next slide. And the third application for machine vision applied to transportation I wanted to introduce is traffic data collection, whether we're talking about speed, volume, and occupancy collection on the freeway. Or
apologies for this. It's
no problem. I know the slides by heart. I can comment the slide I'm not seeing. And another way to do traffic data collection is to also provide a queue measurement, for example, at a tollway, at a toll booth, so that you could get real-time queue information to toll operations, so that they could adjust the number of open lanes, or reshuffle the lane assignments dynamically to adjust to the demand. All right, let me see what my next slide is.
Apologies.
No, don't worry.
Next slide, Eric, is next expectations, right expectations.
Yes. One thing that is key to machine vision, and Eddie had a slide on the performance. So what kind of performance we can expect from a machine vision system. What is very, very important is to set up right the expectations of the end user. Everybody has in mind those TV series or movies, futuristic, where we see people being tracked from one camera to the next, and face recognition and things like that. That's what we, the kind of expectations we have to face every day, and that is typically very unrealistic. But more seriously, what we do is we see there is a big gap between what people think that they can get out of machine vision and what you can actually provide. Even with the best world-renowned systems, we have experience with 700 sites deployed around the world over the past 15 years. Traficon has the same kind of experience, but even with that, sometimes you have a hard time conveying your experience and convincing people that what the right expectation should be, depending on their site, on the particular conditions. So it's very important right at the start of the project to set the right expectations. I saw on the talking points. I saw in the talking points question: is machine vision better or worse than human vision? And I would say, in a few words, nothing beats the human vision. If you had one man, one camera to monitor, the human eye would always be better. However, we don't have 1,000 eyes, so that's where the machine vision comes in handy. It's a good assistance for people who have to manage several hundreds or several thousands of cameras. But there will always be a human being in the loop for incident detection, for example, to validate whether an incident is valid, is serious, or needs what kind of assistance. Let's go to the next slide to conclude. That's the development we can expect in machine vision in the next couple of years. The most important turnaround I will see, because I think the switch from analog to IP is already in the past. It's most of the projects are now done with IP, but the real change is going to be that most of the detection is going to be edge detection, which is inside the sensor or inside a smart camera, and that will enable us to have very wide projects, deployments over very wide distances and stretches of highways, and that we'll be able to do that because the detection being at the edge, we will save a lot of bandwidth. So that will enable us to deploy thousands of detectors without any communications problems. And I see this, whether incident detection had been applied mostly in tunnels in the past, I see the future really in managed lanes, HOV, HOT lanes, making the, if we're going to invest some money into the development of those managed lanes and dedicated lanes, we need to run them as efficiently as possible and keep them from congestion. So machine vision is going to be really key to maintaining those structures running smooth. That's it for me.
Wonderful. Thank you very much, Eric. I really appreciate that. Interesting point about machine vision versus human vision. I'm afraid if it was machine vision versus McQueen vision, then I don't think I would come out too well without my spectacles, and I'm very myopic. So I guess there's a point about human vision being better only if corrected. So next up we have Todd Creter, who's Vice President for Product Development for Iteris in sunny California. So I'd just like to hand over to Todd. So what do you think?
Thank you very much, Bob. Good afternoon. Good morning to everybody. Next slide, Bob. So as Bob mentioned, I head up the product development group at Iteris. And Iteris is a company that is well known for the video detection, traffic intersection products that we develop. But in addition, we also have some different groups that are doing performance measurement type of software, as well as a whole services and consulting area of the company. So really we're a reasonably broad and diverse group. We've been in the traffic and specifically the machine vision, video analytics operation for many, many years. Next slide. So as a number of my colleagues have mentioned, machine vision has been in the transportation area for many, many years now. And one of the things that I think is really important to note is that it's not a new technology. It's been around for a long time. It's one of the most tested technologies there is out there. Numerous studies have been done to prove its effectiveness. There are over 250,000 detection cameras in the field just in the traffic business, not even including all the other machine vision applications we've talked about today. Iteris itself has over 100,000 cameras out in the field all around the world. Next slide. And as mentioned, there are a number of different applications out there. Machine vision is used really all over the transportation arena. And as was mentioned already, some of the newer applications with pedestrian detection, bicycle detection, some of these other types of, we call them vulnerable road users type of things that are happening out there in the marketplace. But it's used more and more each day. and everywhere throughout the industry. Additionally, we talked all about fixed applications, fixed mount, typically fairly fixed mount, sometimes pan, tilt, zoom. But additionally, cameras on cars are also coming along, as we know with our backup cameras, but also other vision cameras for doing types of sensing coming along. So there's lots of things happening in the whole machine vision world. Next slide. So what is machine vision? And as we've talked about, it's really extracting information from an image. Typically we use video images, but it's really teaching a computer how to try to represent what the human eye does. And as we talked about, the human eye is really an interesting camera in and of itself, and it takes very high resolution images or pictures. But the real key to the human eye is the brain that's behind it. When we walk into a room, we can walk into any room in the world and know that it's a room because of the four walls, the ceiling, etc. We can see a car we've never seen before and know that it's a car. That's really our brain that's doing that process. As a computer, we have to teach it what all the different pixels mean, and when the pixels connect together, what the lines mean, and everything else. And so it's really a tough problem, but one that all of us in the industry have been working on for many years and have gotten very, very good at, to be able to teach a computer. The thing a computer does that the eye can't do is that it stays trained on the image. As humans, we lose focus and we lose attention. But machines are extremely good, 24/7, looking at the same image over and over and over again and doing it repeatedly. And that's really where the machine vision comes in, so helpful compared to what humans can do. Next slide. There are other sensors out there, certainly within the traffic and transportation business. Some of them they all have benefits and trade-offs and negative aspects to them, positive aspects to them. We believe machine vision, and I think everyone on this call believes that it has some enormous benefits. I'm going to talk about those next. But there are certain situations where other sensors are the right thing to do. And we'll talk a little bit later about blending some of that. Next slide. Machine vision. When we look at the advantages of using video and video detection in computers, video, first of all, is a wide area sensor. It's not a point technology. It's not a loop in the road telling you what's going on at one place in the road. It has the ability to see the entire scene, to see all the cars moving, to see their speed, to see the queue, as has been mentioned, to see pedestrians, bicyclists, to see the different types of vehicles. And so machine vision has enormous, enormous potential as well as performance in terms of being able to do things. It's a really incredible technology, as well as has been mentioned. You get the image, and there's nothing compared to that image for a human, because the human can see the image and even build upon what the machine can do in terms of being able to see what's going on in the image. Next slide. There are a lot of things happening with machine vision. Enormous changes in the past, certainly in the past 20 years, 15 years, 10 years, but even the past 5 years, there have been enormous improvements in machine vision technology. The cameras are better. They have now what's called a wide dynamic range cameras, which can see into shadows, which suppress glare. Heater technology, glass coatings, reduced amount of maintenance needs on cameras. It all has changed dramatically. If anyone has had, very old experience with machine vision, they may have seen some of the limitations. And I would have to say at this point that the vast majority of those are completely gone, and machine vision is truly the ultimate sensor at this point. Next slide.
2 minutes, please, Todd.
Thank you. One of the things that's really starting to move forward is sensor fusion, using multiple sensors. Machine vision does enormously good things with video, but when you marry it with a radar sensor, we can see that there are different things that can be achieved by marrying two sensors together, by overlaying a radar detection on a video image. Video is extremely good at seeing things and seeing what's happening in an intersection or a situation. Radar can have some long-range properties that vision systems don't really have. And so radar can be married with it, and this is an area that's growing and it's very interesting as we move forward. Next slide. So video detection, machine vision. we believe has enormous benefits. Obviously you get the detection. We've talked about the high accuracy rates, accuracy that's equivalent of loops, even better than loops. But also you get the video image, easy to install, life cycle cost is low, great growth potential. You can upgrade it, you can add features to it, and it's green. You don't have to cut into pavement. You don't have to do a lot of other kind of unnatural things to be able to put a sensor in. Next slide. And lastly, just mention that, as I mentioned, we are Iteris, build a broad range of hardware and software products. We've been in this market for many, many, many years, producing products. I'd say a vast majority of our first products that we produced are still out there in the market operating. Some of my colleagues have talked about that the products last 10, 15, 20 years and continue to produce things. And as always, coming out with new innovations and new solutions, as we've just recently done with Smart Cycle with bicycles and Smart Span working on span wires. And with that, I thank you all. And that's it, Bob. Thank you.
Thank you very much, Todd. I appreciate that. Interesting, the exciting development on fusion sensors, blending different sources together, and also, maybe not too many people think about it, the green aspects of machine vision. I think that was excellent build on what we heard before. I want to hand over to Frank Long now, who's with JAI Traffic Solutions. Are you there, Frank?
Hey, good morning. I come to
Good morning. Over to you.
In the cleanup spot here, but I have a unique perspective of having spent about 20 years in the industrial.
Oh, we're kind of losing you there, Frank. You might need to get a little closer to the microphone.
Okay, how's this?
There we go. Wonderful.
So the unique perspective is having done vision for over 20 years, and then more recently, for the last 7 years or so, having done exclusively ITS applications. Would you turn that page, please?
You're still fading in and out, Frank. Not sure if it's just me. Gareth, are you having the same problem?
No, yeah, I'm having the same problem as well.
Okay.
Is it better now? I'm at this point on the headset.
Yeah, we're hearing you, but very faintly.
Key microphone.
Yeah.
Can you hear it better? I'm seeing full scale on the audio side here.
Well, that's better. I think what you're doing, Frank, is you're demonstrating the advantage of machine vision over audio.
That could very well be. So if you turn the page, please, you'll see some of the technical applications that were presented by some of the colleagues.
Yeah. Bob, can you?
You're fading.
Yeah, I can't.
Yep. Fading to infinity, Frank.
I tell you what we might be able to do here, Bob, is I know we do have one person that has raised their hand to ask a question. I wonder whether we could maybe get that one asked now, possibly, whilst maybe Frank tries to, I think Frank is not dialed in, so I wonder whether he could maybe dial in rather than, just check.
Okay. So,
Yeah.
Frank, could you maybe switch to the alternative mode, maybe dialing into the conference, and then in the meantime, we'll do the equivalent of tap dancing and telling jokes.
Right. In which case, let me. We've got a couple of questions in. In fact, there was we had one that came in before the event from Rob Roush, and we also have one from Armand Ciccarelli. Now, hopefully, if they've got microphones, let me just try and unmute. Okay.
Yeah, I think, Gareth, if you could ask Armand's question first of all, because I think the other question from Bob Roush may well be controversial and might lead to a bit of discussion.
Okay. In which case, Armand, can you hear us? And can you speak to us, more importantly?
Yeah, I can hear you. Unfortunately, you'll have to excuse me. It was an inadvertent question on my part. I'm using my phone to do this for the first time, and I hit the question with my accident. So I don't, in fact, have a question, but thank you for your awareness.
Right. No,
He doesn't have a question.
that's absolutely fine. Not to worry. We may possibly. Let me just see whether we have.
Shall I go ahead with the question that came in before, Gareth?
You could do. I think Bob is actually on the line. Did you want him, if he can speak, did you want him to ask the question? Or would you rather...
I think I'll ask the question. I agreed to ask it on his behalf.
Okay, that's fine.
Okay, the question came from Bob Rausch of Transcore, and the question was, actuation detection at signalized intersections has always been implemented with traditional inductive road loop technology, which moves to a failure mode of constant call, which is essential for a calling detector. Video, unfortunately, seems to miss vehicles, which is unacceptable. Is this really an appropriate technology for intersection actuation? So what he's asking is machine vision video an appropriate technology for traffic signal intersection actuation?
Well, this is Eric. I'll take that. This is Eric. I think if the video was inappropriate for intersection control, there would be a lot of unhappy motorists in the US in particularly, and in lots of countries, because it's been widely used. So I think the question of whether the technology is suitable or not is not even on the table anymore. I mean, there might be preferences from one city to the next as whether to use one technology or another, but I don't think it can be disputed that video is a valid technology for intersection control. And loops miss vehicle too. Loops are 97% accurate, and video is roughly the same. The big difference is when a loop is broken, it's broken for a very long time.
Absolutely. Jim, Eddie, Todd, Frank, any additional comments?
Yeah, Bob, this is Todd. I would concur with that, and not only say that, but that through various tests, we've shown video to be definitely as accurate in detecting as loops, and in all conditions. And that's the thing that's really changed over the past 5 or 10 years, is that the algorithms have gotten so good that some of the, I'd say, historical issues with video are just completely gone in terms of weather and fog and everything else that at times have been concerns. But as Eric mentioned, I mean, it is really the standard in the industry now.
Yeah, I think if I was developing a standard for quality of traffic signal detectors, I would like to do a combination of accuracy and availability.
Yeah, this is Eddie, if I can add to that. I fully agree with what's been said by my colleagues there. It has been proven reliability. That's one nice point on Eric, that if loops get broken, it asks a very tedious intervention and blocking the road, which typically takes a long time before it is executed. So you get a very long timeout. Maybe one very small detail on the fact that the loops give a signal that they are not online. We also in video detection, if the image is really bad, and there is also algorithms in those equipment to constant or to see that the vision is not good, it will also give a signal to the controller, which is called a recall signal, so that the recaller then goes into fixed timings. Of course, we try to minimize that, and it should be as low as possible. But also cameras might fail from time to time.
Wonderful.
And then if they fail, it's obvious sometimes to do with the weather, and even that part with the new technology like thermal vision and thermal cameras, we are getting improved performance in those conditions as well.
Thank you. I think our back channel communications indicate that we may have solved the technical issue with the sound from Frank. Frank, are you there?
I'm here again.
That's better.
Wonderful, much better. So back to you, Frank, and sorry for the interruption, but we really couldn't hear you too well.
Not a problem. So in continuing where I left off at, the main differences that we look at between machine vision in the industrial world and the ITS world really do have to do with the applications and the conditions that we encounter. I put up a number of typical applications there that are used in machine vision and ITS applications. If you put the next page, please. One of the key things here is high-performance imaging will always yield better machine vision applications. This is in a typical context of being able to completely control your scene in a machine or in an industrial context. We don't have that luxury in the ITS world. So whether you're mitigating the conditions, adapting to the conditions, the key to this is getting a high-performance image that allows you to take and do more with that content. Turn the page, please. A typical example here is one where if you were to see only portions of this image, you might not get some of the content that's important. Across this repertoire of plates that's shown here, you've got red content, you've got non-retroreflective plates, you've got paper plates. These kind of conditions are all somewhat unique, but I put them together here in a composite so that you can see that in a scene that allows you to see all attributes on a plate, it gives you the ability to do more with that data. Go ahead, turn the page. Typical plate reading is getting more complex as we go. You're looking at applications where there's a intent to have more graphic plates, to have more specialty plates, and these are just typical type of applications where you'll have a variety of colors and backgrounds and plate data, all of which might be indicative of the actual information that's being stored in the DMV records or the registered user information. Go ahead and turn the page. Some of these things, like in this case, is a specialty plate. Attributes like stacked characters. You have font size independence. You've got difference in content, but this entire information is important to being able to detect exactly what that plate is. Taking it from this image to the next picture, please. You'll see that ALPR can do a good job of being able to read this information, detect that content in different font sizes, etc., and then identify, in this particular case, this specialty plate based on the stacked characters. That's not always the case. In many times, you've got to have that additional plate attribute as part of the equation, and that's where complementing things like traditional ALPR comes into the equation. Next slide, please. To keep the theme of the original webcast here, the question was raised, what is machine vision? And essentially, it's the computer-based image processing for the purpose of making a decision. In this case, an automated decision is something that would be real-time, it'd be fast. The software algorithms that are actually driving this, whether they are embedded, as some people have mentioned, or whether they're host-based, it's really irrelevant. It starts with a good or purposefully captured image, and then you're applying these software algorithms to actually interpret that data. Machines can definitely operate more consistently over longer periods of time on larger amount of data. The difference between the human interpretation is that the brain is far better at being able to distinguish the nuance of the image, the context, the entire scene, and therefore what you have to do in preparing for this type of an application is you need to write the algorithm in a way that it's going to not be affected by these other conditions. But there is always a place for the human in the equation, but machines will always do it on a far more consistent basis because it's not distracted. Turn the page, please. One algorithm example of this would be vehicle matching or fingerprinting. Go ahead and turn the page. Typically, a plate read could easily be misconstrued. When you look at the left-hand example there, you'll see a very similar read characters, but notably different content. In an image comparison, as you see on the right side of that example, it also has very similar attributes or symbology there, but different orientation and different content again. What vehicle fingerprint matching allows you to do is to be able to get away from purely looking at it as solely a plate read and using these additional attributes to distinguish the characteristics or the content on that plate. It's a faster and easier task for both a computer and a human to be able to do this type of comparison. It's also extremely complementary to what you might have out of the standard plate read as well. Turn the page, please. A typical fingerprint is extracted from the vehicle information or biometrics that might be there. The most unique identifier in this particular case is always going to be the license plate, but the key to this is that it allows you to have a very small amount of data that's collected it doesn't necessitate the storage of that image in many cases, and it allows it to be processed very fast and very uniquely with a low degree of ambiguity. So a candidate can be encountered, and you can match that with a very closely or identical image at a different context. So it could be night and day, it could be overcast and sunny, but the key attributes will always have a high confidence of being matched. Turn the page, please. This is an example, and in some cases you can actually match a vehicle captured in an actual image from a synthetic image or content, for instance, that might be keyed in. This type of computer-generated image might be something that would be used for silver alerts or amber alerts or other specific searches that are being done in context of trying to identify a vehicle that's on the roadside as well. Turn the page.
2 minutes, please, Frank. 2 minutes.
Next page, please. So this is a typical installation for a section control. This is a Holland-based system here, and in this case, it's a matter of doing speed over distance or time over distance, and looking at capturing a vehicle, matching it to its Section A and Section B entry-exit, and then ultimately using ALPR to identify the registered user and enforce a violation or a fine. Turn the page, please. Here's a simple diagram of the typical situation. I've got a vehicle passing at an entry station. I've got the same vehicle passing at a different exit station. I find the closed-loop candidates that are in there, very accurately matching that, and then doing the speed calculation based on the entry time and the exit time. We turn the page again. This type of a technology can be used for any of these types of applications: time over distance, trip, data collection, amber alerts, tracking of vehicles throughout an operation, and even complementing things like video tolling. Turn the page again. Generally, when you look at these kind of algorithms being deployed, again, you're not looking at having to adapt to every nuance of a plate. In many cases, we've got states with tens and hundreds of different plate styles, multiple countries that would pass borders and things like that as well. It eliminates the need for some of the support or maintenance aspects of the software maintenance. And it also allows it to work even when you have a partially occluded plate that might be temporarily occluded by a trailer or a plate frame, or permanently occluded either intentionally or unintentionally by the operator. Again, this is a technology that allows you to have and preserve some of the privacy of the operators of the vehicles as well. In some cases, in jurisdictions, that's important and even necessary. But it does allow you to say, only if you're a violator do I want to collect or retain this image. If it's non-violation, dispose of that image and let it time out of the system. Go ahead and turn the page, please. As a whole, what JAI does is ITS traffic solutions, and both hardware and software solutions. Look forward to helping anybody that has these kind of needs, and look forward to your questions.
Thank you very much, Frank. I didn't realize my vehicle had a fingerprint until your presentation. Learned something new there. Thank you. And thanks to Frank, Todd, Eric, Eddie, and Jim for fascinating presentations. And Gareth, thank you for the slides. I have to point out that there was a latency between Gareth pressing the button and the slides appearing. It wasn't that Gareth was slow or asleep at the wheel. It was just a computer issue. So over to you, Gareth.
Okay, thank you very much, Bob. I'd just like to say thank you to you for acting as moderator for that, and to thank, as you did as well, Jim, Eddie, Eric, Todd and Frank for giving up their time, and for all of you out there listening to this. Hopefully you found it interesting and informative. We obviously haven't had time for too many questions, and I think there are at least a couple that we haven't had time for. So what I will do is I will try and record these and maybe get some answers from the panelists offline and circulate them to the people that have asked. I think that's about it for this one. If I can maybe just mention that the next webcast should be 2 weeks today on the 13th of June, and the subject will be enforcement. We're just drawing together the final details of that and the panellists, and hopefully we'll be able to get an email broadcast out sometime early next week giving details of that and allowing people to register. So unless Bob has anything else, I think that's probably it from us, and thanks everyone for giving up their time today.
I think, Gareth, the other plug we wanted to make is for the Thinking Aloud podcast that Paul Hutton and I have been working on.
Oh, yes.
Particularly fascinating as
Yes.
we were ITS Canada this week. And
Indeed. Sorry, plug away.
in particular, we had a fascinating interview with the Honourable Stephen Fletcher, who's the Minister of State for Transport for Canada. So I think that's on the Thinking Aloud website rather than the H3B one. Is that right?
That's right. Yes, I have sent out links to it on email broadcasts to the North American audience this week. I will be including it to Europe and the rest of the world as well. Hopefully, in email broadcast tomorrow. So yes, you can go there, and hopefully it will be on the Thinking Highways website early next week as well.
Wonderful.
Okay. Well, that's all I had, I think, Bob.
I think that's it for me too, Gareth.
Okay, well, just thanks to everyone once again for their time, and I thought it was quite informative and interesting, and apologies for the slight problems I had with the slideshow, which I'm sure you probably all noticed. But thanks again for your time, and hopefully we'll talk to you soon.